In this video, I'm going to focus on the trends that can be observed in the periodic tables. In addition, the last few little bits of information, I think you can use a little bit more insight when it comes to some of these last few things from Chapter 8. And so the first periodic table trend I'm going to talk about is the atomic size, or also known as the atomic radii. And so the atomic size in general is going to increase down a group and decrease across a period. And please note, across a period, I mean from left to right on the periodic table. And so the reason why this happens is that as you go down a group, remember the periodic table is set up a way that things in period 1 are in your n equals 1 energy level. And as you go down the going down the group, each additional period is basically just adding on another energy level that you can fill up with these electrons. And so your n equals 1, or the first period, the one includes only hydrogen and helium, you're looking at the n equals 1 energy level. But as you go down to the second period, you're now looking at n equals 2. And because of that, you are basically adding a whole nother layer to this atom in which you can start filling up more electrons. But as soon as that second layer is completely filled up with the 8 electrons, remember 2s2, 2p6, and so as soon as that second layer has 8 electrons, it can't hold any more, so therefore it has to go and create a whole brand new n equals 3 layer. And so in these additional layers, you're pretty much putting electrons further and further and further away from the nucleus. And every time you add a new layer, you're adding new size to this atom. And so everything in in period 1 are going to be much, much smaller than everything going down the group or in period 7. And so decreasing across a period can be seen kind of in an opposite route here. And so as you go across a period, please note that you are not changing your n equals value. So therefore, you're still staying in the exact same n equals, or the energy level, that you were at the very beginning of that particular period. And so the main issue here is as you go across a period, you're adding protons as well as adding electrons. And so in these instances, if you have more protons and more electrons, you're going to have a greater attraction between the two quantities, or between the two particles. And so something that only has one proton and one electron, those are still going to be attracted to each other. It's just going to be a much, much smaller attraction compared to something that has 81 protons and 81 electrons. And so as you go across a period, you are not adding any more layers, and so your atom is not getting any bigger. It's not actually adding any more additional room for these electrons to exist. All it's really doing is just adding electrons into that existing layer. And so as you add protons and add electrons, as you go across a period from left to right, you're increasing the attraction between these types of particles. And as you increase in attraction, as you should kind of note from any magnet you've ever touched, more attraction means the tighter and tighter and tighter these things are going to be attracted to each other, and they're going to start again kind of getting tinier and more condensed because they have a greater attraction. So one thing I do have to note, and reason why I put it in red letters on this picture here, is the fact that even though I'm telling you things get smaller going from left side of the periodic table to the right side of the periodic table, I am not implying that there is going to ever be a metal that is going to be smaller than a non-metal, because everything on the left side of the periodic table is going to be much larger than anything on the right side of the periodic table. And so the smallest metal is still always going to be is always going to be larger than even your largest non-metal. Metals are always inherently going to be larger than non-metals. So the second concept I want to focus on here is what they call ionization energy. And so the ionization energy is the energy required to completely remove 1 mole of electrons from 1 mole of gaseous atoms. So typically, we don't kind of deal with a whole mole of this stuff, and whenever we talk about these calculations, so we can actually narrow our view down to just 1 atom. And so if we have 1 mole of electrons being removed from 1 mole of atoms, it's the same deal as saying 1 electron being removed from 1 gaseous atom. Please notice we're not talking about solids or liquids here, we're talking about gaseous atoms. And that will come up a little bit more in the next chapters that we're going to be discussing. And so when we talk about ionization energy is essentially going to be the opposite of your atomic size. And so, with some exceptions. And so, ionization energy generally decreases as you go down a group and increases across a period. And the reason for this, again, has to do with how these electrons are being input into these energy levels. And so in order to remove an electron, you have to assume that that electron is going to be fairly easy to remove. Because if it's not, again, you're not going to waste the time trying to rip an electron off of something that doesn't really want to let go of that electron. And so as you go down a group, remember these atoms are going to be getting bigger, or the increasing size, as you go down a group. And because of that, these electrons are going to be further and further and further away from the nucleus as these atoms get bigger and bigger. And so as they get bigger, the electrons are further away, they're going to have less attraction towards the nucleus because they're so far away. There's other electrons in between, kind of like, again, canceling out some of this attraction. And so because of that, larger atoms are going to have much lower ionization energies because it's going to require less energy for you to remove that electron from a bigger atom. On the other side, as you go across a period, as we kind of discussed in the previous portion here, the atomic size decreases across a period, meaning the fact these electrons are now getting closer and closer to the nucleus, meaning they have a much higher attraction than the ones in the further away. And so the closer you are to the nucleus, if you're an electron at least, the closer you are to the nucleus, the more attraction you're going to feel, the harder it's going to be for you to remove that electron from that atom. And so atoms that have low ionization energies will typically form cations. And by cation, I mean this atom has had an electron removed from it, and it is now a positive or positively charged ion. And so if you have an electron that is easily removed, then again, it's going to form a positive charge. Typically, these are all going to be metals. One reason is because metals are larger, and in addition to that, these metals typically only have 1 or 2 valence electrons, and so they're much easier for you to remove these electrons from. On the other end, things that have high ionization energies typically form anions, because something like fluorine, for instance, fluorine really loves electrons. It loves electrons so much it's never going to get rid of its own electrons. It won't let any other atom take its electrons from fluorine. But it loves electrons so much that it's willing to take somebody else's electrons. And so in these cases, fluorine will always end up being a negatively charged ion because it's always going to accept electrons and it will never get rid of its electrons. And so what I mean by high ionization energy, I mean it's going to require a lot of energy for you to make this thing into a positive charge. It's going to take a lot of energy for you to remove an electron from fluorine or from any of the noble gases. And so please note here that, or sorry, not noble gases, halogens. Please note here that noble gases typically don't have ionization energies because they just don't want to get rid of electrons, gain electrons, or anything like that. And so the last thing that I have in purple here is I need you to understand the exceptions. And so I have some slides in my, I have some, again, 2 or 3 slides that discuss this in my slides that I posted on Blackboard. But you need to actually kind of understand where these exceptions are coming from. And so what I mean by exception is typically these ionization energies tend to follow a very linear relationship. The bigger they are, the more energy, so on and so forth. But there are some exceptions to this rule, meaning the fact it does not follow that linear graph that is being depicted. And so the exceptions are always going to come into play whenever you're trying to destroy something that has a very stable electron configuration, or you're trying to make something that is unstable into a stable form. The 2 exceptions I have here, again, are a little bit different than the exceptions I have in my slides, so please look at both of them. Hopefully it'll make a little bit more sense. And so the exceptions here I have is phosphorus and sulfur. And so if you take a look at phosphorus's electronic configuration, you'll notice that 3s2, 3p3 is relatively stable. And the reason for that is because your 3s2 is a completely filled completely filled s orbital. Your p3 is a half-filled orbital, in which the case will be a lot stabler. And so whenever you try to remove an electron from 3s2, 3p3, it's going to take a lot of energy to do so because you are essentially trying to destroy a stable atom. And so here, phosphorus is going to try to fight that. And so you're going to have a much tougher time removing one of those electrons from the 3s2, 3p3. Well, on the other end, sulfur. Sulfur is 3s2, 3p4. And so here, your s orbital is completely filled up, and your p orbital is actually one electron too many from being halfway filled up. And so if you were to remove an electron from 3s2, 3p4, you would end up creating 3s2, 3p3. And as I stated with phosphorus, that's stable. And so sulfur is very, very willingly going to give up one of its electrons in order to make a completely filled, half-filled orbital here. I'm sorry if you're getting some background noise here. The trash truck is outside right now picking up all the trash. And so the last one I want to talk about is the electron affinity. So electron affinity comes into play when we start talking about the energy changes that accompanies the addition of an electron to a gaseous atom. And again, by the strictest definition, it's the addition of 1 mole of electrons to 1 mole of gaseous atoms. But here, I'm only interested in 1 electron, so I'm going to say the addition of 1 electron to a gaseous atom, 1 gaseous atom. And so if you check out the slides I posted on Blackboard, you notice that I'll say something along the lines that electron affinity does not have any real guidelines, meaning the fact it doesn't really necessarily decrease going down a group, increase across a period, or anything like that. And so electron affinity has so many exceptions that we can't give a general rule because there isn't really one generalized enough for it. But the two ideas that you need to keep in mind for electron affinity is if you have an atom that has a low electron affinity, it is going to form cations. And by low, please note I kind of mentioned here, and I'm talking about magnitude. Most of these things, again, we're talking about adding electrons. Electrons are negative, so most of these energy changes are going to be negative as well. But I'm not saying low electron affinity like negative 1000 is not going to be less than negative 100 when I'm talking about magnitude. Here I'm just saying look at the value. So look at the 1000, look at the 100, ignore the charge in front of it. And so things that are low electron affinity, that means they like electrons. And so in that case, they're going to much more willingly accept these things, or kind of accept the fact that they're not going to hold on to these electrons. They're going to want to get rid of them. They don't want their own electrons. I mean, hell, sodium is always going to be a +1 because sodium doesn't like electrons. It doesn't like electrons so much, it tries to get rid of its own electrons. And so things with low electron affinity do not like electrons. They have a low attraction to them. So therefore, they're always going to typically get rid of electrons rather than accept electrons. Whereas if you have high electron affinity, that means you love electrons. You would love for electrons to be added to your atom. And so in these cases, these things will typically form anions, or negatively charged particles. The exceptions here are basically the same exceptions to the ionization energies, except they're kind of backwards. And so here is something like silicon, 3s2, 3p2. This is much more willing to accept an electron in order to become 3s2, 3p3, or full s orbital, half of the p orbital. Whereas phosphorus, as I kind of stated before, it's nice and set in its ways. And so if you try to mess with it by either taking an electron away or adding an electron, it's going to start messing with the stability. And so therefore, you're going to have to pay a little bit of a charge when it comes to it. And again, you'll see this in terms of energy levels kind of going up and down. And then last but not least, your noble gases. So noble gases are the ones that have completely filled electron shells. They're completely filled s orbitals and p orbitals. And so there's no way that any of these noble gases are ever going to accept an electron willingly.